Welcome again to Computational Fluid Dynamics 2024. Got a smaller class today. Apparently, we scared everyone last time. All right, but it's a fun journey, so let's begin. Today, my objective is to derive the Navier Stokes equations, which are the equation set which is the equation set that we are going to be working with throughout the semester, most of the semester. Because if you know how to solve those, then other variations of these equations will be easily doable, because these are the hardest demonstrably, because there's no equation for the pressure. And I'll get to that point once we do the derivation. Now, it is usually assumed that for someone taking this course to know the equations of fluid dynamics. It's called computational fluid dynamics. It's a grad level course, right? So you'd at least expect it to know those equations, but it's always good to have a refresher of those equations. And if you haven't seen them, it's a good opportunity to see them today. And this year, I'm going to take a different perspective to derive those equations. For those who took fluids with me last year, we spent over 2 months deriving the full equations. We did Reynolds transport theorem, integral form, differential from the integral, and viscous stress tensor, etc. I'm going to do all of that today in 1 hour, 1.5 hours, just by leveraging some chemical engineering perspective on these equations. Okay, there'll be some assumptions to be made, but they will be very consistent with incompressible flow and constant density flows, which we are to work with. Okay, now the basis of CFD are conservation laws, such as conservation of mass, conservation of momentum, and conservation of energy. Those are the 3 primary guiding principles that will help us develop a mathematical model to solve in CFD. Okay, so I'm starting kind of even before fluid dynamics. The fluid dynamics equations themselves are based on conservation of mass, conservation of momentum, plus or minus conservation of energy, depending on whether you have energy transfer or not. Okay. So, and I have a note here that you need to master these principles and the corresponding equations eventually, otherwise you'll mess up any implementation or interpretation of your results. Welcome, guys. Okay. Now, when you think about the great conservation laws, when we say, Newton's second law, that summation of forces equal mass times acceleration, or when you look at first law of thermodynamics, etc., those kind of just give you the differential equation, right? M du by dt equals summation of forces. So we can just apply that to a fluid. Unfortunately, the issue is that all of those conservation laws, mass, momentum, energy, whatever other conservation law, they are applied to a system, which is a uniquely identifiable piece of matter, like a particle or a planet or a rock, right? Everything is there together. So when you apply momentum on a car, Newton's second law, it's the entire car, right? You're not applying it to the little particles inside the car, etc. Even if you do that, right, you would have those laws would apply on individual pieces, not on individual systems, okay? And that is going to pose a problem for fluid mechanics, because fluids, the only way to do it in a fluid, you can't just take the whole bulk of fluid and apply. I mean, if you do that, let's say you take a pipe flow, for example, and you apply Newton's law on it, that's only going to give you the net force on the pipe. But what if you want to understand what's going on inside the fluid itself, at every point inside the fluid? You would need to isolate every fluid particle, the smallest particle possible, and call that a system, and then apply Newton's law on that. And I'm describing these here by these little parcels over here, or these kind of larger elements. Okay, so I call those fluid particles or fluid elements. So I want you to think of that carefully, right? So when you take Newton's law and apply it, if I'm applying the Newton's law to the table, okay, that is going to work over the entire table, because that entire table is moving, right? But when I apply this on a fluid, I either apply, which would just be the net force on the pipe, but it doesn't give me any information about inside the fluid. If I want to apply Newton's law inside the fluid, it has to be applied to individual particles. And each particle has to have its own identity. Like you have to track this particle everywhere it goes, etc. Now, this is problematic because from a computational perspective, or even an analytical perspective, you would need hundreds of millions of fluid particles to statistically correctly represent a flow in a pipe. Now imagine representing flow in the ocean or flow in the atmosphere. You would need tens of trillions of these little systems, right, to describe what is going on. So think about two galaxies merging and looking at each star in those galaxies, right? You would have to solve the Newton's law for each one of those stars. Same thing here. You would have to solve Newton's law for each one of those particles. So that becomes extremely complicated. Eventually, we might be able to do that. And there are methods like smooth particle hydrodynamics that say, OK, I'm not going to take the smallest fluid system or fluid particle. I'll take a collection of maybe 1,000 particles and call that my system and apply Newton's law on that. And you know, it gets us somewhere, but it's not as robust as what we're going to learn here. Fortunately, there's another way around it, and it's simply a change of reference frame. So the first frame that I was talking about is called the Lagrangian reference frame. And if you haven't heard of that before, you are essentially riding on a roller coaster in the fluid. So you pick a particle, you sit in it, and you just move with it. And then see things coming at you and hitting you and moving at you, and you're spinning, right? And that's what it would be like if we were to apply Newton's law directly on each particle in the fluid. But again, that's intractable. That's very expensive. So we would need another that would allow us to instead say, no, I want to step out of this fluid and look at it like we're looking at it here and say, OK, what happens? I don't care about tracking the red particle or the orange particle or the green one or the purple one. What I care about is when this particle, when the fluid comes through this point in space, what is its velocity, its temperature, its pressure, its density, for example. So that's called an Eulerian reference frame. Rather than riding with the system, we leave the system alone, step out of it, and we focus on a region of space and say, what happens to the fluid in that space? Then the assumption is, for any arbitrary particle that goes through the system, it will either pass on or inherit the properties of what's going on at this point. Okay? Just by doing that, it saves us immense computational power, because now we don't have to track millions of particles. Instead, we could track a few hundred grid points in the domain, okay, a few hundred points. The curse, though, the price to pay, is that now you have convection. So once you transfer from a system transformation, and for those of you who don't see that yet, that's OK. Once you take kind of fluid mechanics, you'll understand that the notion of this material derivative, the change. If you're riding with a particle, you don't see advection. You only see change in time. You don't see change in space. That's Einstein's experiment. You're riding in an elevator, OK, closed. You just see change in time. You don't see change in space, right? But once you step out and watch someone riding in that elevator, then you see changes in space as well. And that shows up as what we call advection, really. And so the price to pay is that we have a nonlinear term called advection, and it adds that complexity to the equations, okay? So we call that typically control volume, and the surface, the edges of the control volume are called the control surface. All right. So now our objective is, okay, what can we do about, again, we're trying to develop the equations that govern this fluid so we can solve them on a computer. Okay? And we're going to take many control volumes, hundreds of small ones or a big one or two large ones, whatever, right? The same methodology is going to work. And we're going to adopt a simple approach to derive our governing equations. I was saying before you came in that there are numerous ways of deriving the fluids equations. And if you listen to my fluids lectures, you'll see I go through this theory of Reynolds transport. We do it in integral form because there's really, truly only an integral analysis when you're approaching systems, and then we derive the differential analysis from the integral system. It's the stronger form of deriving these equations. And you could spend 2 months on doing that. There's another approach also that's kind of quite common in chemical engineering, and that's what I want to try to do today. So this is the first time I teach this approach, so I'm probably going to make a mistake. Please call me on it. And if not, that will be hopefully a good success. But the idea is, I want to use the idea of a balance of a quantity inside this control volume, aka conservation of a quantity. Like what's coming in needs to be accounted for. What's coming in, what's leaving, and what's staying inside that control volume, plus any forces on the control volume. Okay? So, for example, for a pure non-reacting fluid, so that's just water, for example, total mass conservation, the law of total mass conservation says that in any piece, in any chunk of region of space, whatever is coming in, okay, must be balanced by whatever is leaving, and also whatever is being left inside that space. So if it's not compressible, then nothing is going to be left. Whatever is going to come in is going to leave. If it's compressible, maybe some of it is going to be left because you're compressing it. So what goes in is not necessarily equal to what goes out, but it's balanced by how much you add in that region. Okay, that's a general conservation law. Once you see the math, it becomes easier, frankly. Okay. So we will consider a general fluid with the following properties or the following nomenclature. We will call we will designate a velocity vector field at every point in space. So when I say that the velocity vector field at this point is u1 vector, so it has three components, u, v, and w components, okay, and x and y and z. Okay, so that means that any fluid particle that touches that point immediately inherits that velocity. Okay, so that's our Eulerian perspective. Now, in general, this velocity field is u. It changes in space and in time. It's a vector field. Every point in this fluid has a velocity vector, and it's different from point to point. And each velocity component is a function of the entire space domain, x, y, z, and also in time. It changes in time. Okay, so we say this u is equal u of x, y, z, and t. Okay? The fluid is going to have a density rho, a viscosity mu. If you don't know what viscosity is, it's just essentially resistance to motion. It's like when we talked about heat transfer coefficient. The larger the heat transfer coefficient, the more heat can be transferred, the smaller. This is kind of the opposite. The larger the viscosity, the more resistance the flow is going to have to motion. So, for example, molasses has higher, or oil has higher viscosity than water, which has higher viscosity than air. Okay, and then pressure. Okay, just wanted to set this nomenclature here because we're going to start seeing it in a second. Okay, so here's how we're going to derive the equations today. Try to pull it off in 1 hour. The idea of transport. Okay, in all natural systems, there is movement of information. Okay, information is being moved. This information could be mass, could be temperature, could be concentration, could be sound. Okay, could be electromagnetic waves, could be light. It's just information. Information is an umbrella to everything. Now, different pieces of information, some of them are related to matter, some of them are not matter. They're actually waves. They don't need like a physical space to transport. But, you know, it's still the same idea, this idea of transport. Now, we will consider a small fixed control volume. I drew it here in 2 dimensions for simplicity. We'll do the 3D in a couple of slides. And I want you to consider a small control volume with some initial amount of information. Okay? Now, let's call that information phi. It's our commonly used dummy variable name. Okay, phi is just could be any kind of information. And typically, this phi, or by definition, this phi should be per unit volume. We'll understand that later when we derive the equations, because this volume is arbitrary. If you make phi dependent on the volume, then it's going to change for a different volume. But if you make it per unit volume, then it doesn't matter what volume you choose. Right? So that's why we make it per unit volume. I could have drawn this as a circle. Doesn't matter. Phi is a quantity per unit volume. Okay, what are some examples of phi? Okay, mass. What is the equivalent of mass per unit volume? Density, right? Okay. Density is one version of phi. It's mass per unit volume. So there you go. That's one piece of information. Hint, hint, is going to be related to conservation of mass. Okay. What about momentum? What is momentum per unit volume? Momentum is mass times speed, or velocity, mu, divided by volume, it becomes rho u. So rho u gives you momentum per unit volume. Now remember, this is a vector here. U is a vector, and that's fine. Phi could be a vector. It's okay. It just has three components, rho u, rho v, and rho w. Okay? Total energy per unit volume, rho times E0. E0 is energy, okay? So, okay, great. So we have this phi, which is units of phi or dimensions of phi per unit volume, okay, per cubic meter if we consider SI units. Okay. Now in material systems, okay, so now we're starting to narrow down to the real world, not electromagnetic waves, etc. Material systems where there's matter. There are two primary mechanisms that move information in and out of any region of space. Can you tell me what those are? Advection and diffusion. Okay. What can you say about advection? With the fluid velocity, with the bulk, yep, with the fluid velocity. What about diffusion?
It's trying to smooth things out.
Okay, but how does it communicate? Like the mode of communication for advection is the bulk fluid velocity. I'll explain that in a second. But the mode of communication for diffusion, so think what did Einstein prove when he did his dissertation? He looked at these pollen grain kind of moving and vibrating and shaking and transferring information that happens at the molecular level. It's a completely different phenomenon, okay? All right, so your colleague is right. There are two mechanisms that, that move information in and out any region in space and material system. The first is called advection or convection. Same word, I'm going to use those interchangeably. And it's essentially the movement of information. Again, information could mean concentration, temperature, mass, pressure, whatever, okay? It's the movement of information by bulk fluid velocities. Simple example, okay? I have an incense stick here, and you're standing there, and the incense is going to go out, up, etc. You blow a fan. What happens almost instantly over there? You're going to smell it. What happened? That wind transported the concentration of the incense smell and moved it all the way over here. Okay? So that is advection. It's motion by a fluid velocity. Okay? So information in a fluid flow, information including mass and momentum and energy can be brought in and out of a control volume by convection or advection. Now technically, and I mentioned this a minute ago, advection is just the result of a change of reference frame from Lagrangian to Eulerian, because advection doesn't show up if you are riding with the fluid particles. If you're riding with the fluid particle, you're just moving, if you were riding with the fluid particle here, you just inherit that sense of incense and you just move. It just diffuses out as you're moving, but there's no convection into it. Okay? Now the other mechanism is diffusion, and that is the movement of information by molecular communication. Advection is strictly macroscopic and diffusion is strictly microscopic. Now diffusion, we learn it goes from the high value, and you need a gradient for diffusion, like when you put ink in some water, it starts diffusing very slowly. Right? It goes from the high concentration of ink to the low concentration of ink, and then it eventually diffuses everywhere inside that liquid, right? So that it equalizes everything. Like Adnan was saying, it tends to smooth everything out, nice and easy, right? And that's what the diffusion does, but it occurs at the molecular level. Now, at the molecular level, particles are exchanging information left and right. They could go against the gradient or with the gradient, but the net effect that we observe is that diffusion occurs always from high value to low value. Yes?
So could that be both energy and concentration or mass?
Yeah. The mass does not, bulk mass does not diffuse. I'm going to get to that. But if you have a multi-species problem, you could diffuse mass between different species, but the net mass of the system does not diffuse. But diffusion then becomes more important for momentum, for energy, and other mechanisms. Yeah.
So is that like, so if we
Yes, but through molecular communication, not with the fluid, not with the fluid velocity. Okay. All right. Okay. Okay, great. Now, as information, okay, sorry, I had this, okay, here. As information moves in and out of the control volume, some of it might accumulate, adding to the existing amount of phi. So remember, we started with some initial amount of phi, could be 0, could be some initial value. Or it might deplete it. If more is coming in than is leaving, then it's going to add to phi. If more is leaving than is coming in, then it's going to take out of phi. Okay? So that's a general way. That's an account. We're just doing accounting for phi. And that's really what conservation is about. You're taking account of everything that's coming in and leaving. So we can therefore make a mathematical statement about the rate of change of this information, phi, inside the control volume. And we can simply say that the rate of change of phi is balanced by net advection and net diffusion. I didn't put signs here. We're going to get to the signs in a minute. But like if the net effect of advection and diffusion is going to draw things out of the control volume, then d phi by dt is going to be negative. It's going to decrease over time. If the net effect of advection and diffusion is to bring in more info to the control volume, then d phi by dt is going to increase. If the net effect is 0, then it's not going to change. d phi by dt is going to be 0. Okay? Now, to account for non-conservation situations or things that are a little bit different than just net advection and diffusion, such as when we get to momentum conservation, we need pressure forces and gravity. We need to introduce some other ways to make a change inside that control volume, not only by advection and diffusion. There are other things that could happen. There could be a gravitational force causing motion inside, change in phi inside that control volume. So we just simply add a source term, okay, to account for non-advection diffusion effects. Okay? Great. All right, let's get into some more math. Advection and diffusion bring in or take out information through a control volume in the form of fluxes. What's a flux? A flux is simply the rate of movement of a quantity per unit area per unit time. So it's that quantity per meter squared per second. Okay? Now that meter squared is very important, as we will see later. But that's what a flux is. It's simply dimensions of phi, could be rho or rho u or rho e naught, okay? Dimensions of phi per meter squared per second. Now, this automatically allows us to define the advective flux and the diffusive flux. We'll start with the advective flux because it's unique. There's only one kind of advective flux, and that's simply u times phi. Okay? U times phi. Okay, I have a mistake here. So this is yeah, I have a little mistake here. I'll fix it next time. But anyway, so this is the advective flux. It's u times phi. It's transporting phi by the velocity field u. Okay, that's our advective flux. Okay, that's the advective flux. It's transporting phi by the velocity field u. Right? There's only one advective flux. Now for the diffusive flux, there's a lot of diffusive fluxes. Okay, I'm only going to talk about one diffusive flux that you're probably familiar with, which when you studied the heat transfer, you said that the heat flux is equal to minus k times the gradient of temperature. Okay, why? Because you want heat to be positive, because when the temperature is higher than the lower temperature, then the slope is negative. So grad T is negative. So you multiply by a negative sign to make it positive, so that heat goes from higher temperature to lower temperature. That's called a Fickian diffusion law, Fick's law of diffusion. And it also applies to generic information. The simplest diffusion law or diffusive flux that you could put together is simply minus some coefficient times the gradient of the information. What this says is, so this gradient is a vector, obviously. So if in 1D, this would be d phi by dx. So this is saying minus some coefficient times the gradient of phi. And that enforces the idea that the diffusive flux is positive if you're going from high to low. Because when you go from high to low, d phi by dx is negative. And you multiply by another negative sign, you get a positive quantity. So flux, diffusive flux is positive when you're going from high to low. Okay? And that's in our convention. Okay? So that's why you always put a negative sign in front of here. Okay? All right. Oh, yes. No, I didn't make a mistake. My bad. My bad. Sorry. So this is correct. I forgot. Phi is phi per unit volume, right? It's unit dimensions of phi per cubic meter. And this is meters per second. So that makes it units of phi per meter squared dot second. All right. Same thing here. The units of k absorb things because gradient is 1 over length, 1 over meter, times unit of phi of meters cubed, and then k is going to absorb all of that. Okay, whatever the dimensions of k will adjust so that the flux is correct. Now let me give you actual practical examples. For the advective flux, let's start with the mass advective flux or mass convective flux. For mass, phi was rho. Remember? We said that phi is rho. So the mass convective flux is simply u phi or rho times u. And then if you plug in the units, you get kilogram mass. That's the information you're moving. The flux of mass is kilograms per meter squared second, dot second, okay? Per meter squared per second. The x momentum convective flux, what is x momentum? It's rho times the axial velocity u. But then you multiply that by the vector u, okay? You do all the math, you get momentum, which is mass times velocity. This is dimensions of momentum, right? Kilogram dot meter per second. So mass times velocity per meter squared per second. Okay? See how consistent this is? It's beautiful. Y momentum diffusive flux, same thing. What is the Y momentum? Phi for Y momentum is rho v. Remember, this is momentum per unit volume, rho v, times the full vector field. Okay? You're starting to see nonlinearity here. And again, it has the correct dimensions. Momentum per meter squared per second. Now for the standard Fickian diffusive flux, you get momentum diffusive flux. Okay, you have minus mu grad u, okay, for the momentum diffusive flux, and that has the dimensions of momentum per meter squared per second. Okay, and for the heat diffusive flux, now heat is not temperature. Temperature is not conserved. Heat is conserved. Temperature is only a surrogate for heat. But we still can come up with a diffusive flux for the heat equation through temperature. And it's minus k grad T, which is energy, joule per meter squared per second. Okay, so everything is well with the world. Okay, great. Now, as you've seen here, the flux is actually a vector quantity. Rho times vector u is a vector. Rho u times vector u is a vector. Rho v times vector u is a vector. Mu grad u is a vector because grad u is a vector. Grad t is a vector. So all of those are vectors. So in fact, the flux is a vector and has components in all spatial directions. Otherwise, information wouldn't be able to go in from all and leave from all directions. So we want the flux to be a vector in all directions, coming in and leaving from all possible directions. So we will write this in general as the flux J, and the x component of the flux is J1, y component is J2, and the z component is J3. Okay? So for example, the advective flux u phi, vector u phi, is axial velocity, so u phi times I, v phi j, w phi k. So it has 3 components. Okay? And all of those, they change in space and time. Okay? Same thing for the diffusive flux, minus k grad phi. Again, substitute whatever you like in place of phi. Okay, put rho or rho u or whatnot. Okay, excuse me. And then you get that. You have the 3 components of the diffusive flux. All right. Now, okay, so now we have fluxes, and we have these loose ideas, the idea of conservation that the rate of change of phi inside a control volume is related to the net advection and net diffusion, okay? Now, we're getting close to computing the net advection and net diffusion, but we don't have the units quite correct yet. Because d phi by dt is units of phi per cubic meter per time. And even you multiply that by the volume, which is the control volume, you get d phi by dt only, essentially. So you get units of phi per time. And, you know, that's, well, yeah, if you multiply, yeah, you get units of phi per time. And that's not quite consistent with units of phi per meter squared per second. So we need to knock out that meter squared in the flux calculation. And in reality, the flux is really just an imaginary way as a step towards doing correct math. To calculate the net amount of convection and diffusion that's coming and leaving a control volume, you have to define a surface, an area that the flux is going through. And then, by multiplying the flux with the area, you knock out that meter squared, so you get phi per second. So you get consistent units with d phi by dt. So a flux is only like if you think about it, like, yeah, the flux at this point is this much per meter squared per second. But once you define a surface, then you compute how much of that quantity is coming in, because you need to define an actual area, and the orientation of the area could be different. If you have flow coming in and you put an area, the whole thing is going to go in. But if you put an area, a surface like that, not all of it is going to go in, right? So you have less amount of information going in. So we need to define a surface. And in general, so this would look like something like this. The red vectors over here are the flux vectors. And this is a surface that we've arbitrarily defined. And it has unit normals in this. If you don't know what that is, don't worry about it for now. The unit normal defines the normal orientation of the surface. So in general, to compute the rate of phi that is going through a surface, you need to take the integral of the flux with the unit normal of that area and integrate over the entire area. Okay, so let me demonstrate to you that this actually has units of phi per second. Okay, so J is dimensions of phi per meter squared dot second. Okay, dimensions of phi, like mass. Well, this is technically wrong. It should be dimensions of the surrogate for phi, so mass or momentum, right? So this would be kilogram per meter dot second, let's say, for J, times meter squared, which is the area. So that gives you dimensions of phi per second. Okay, that gives you a rate of phi that's coming in, not per unit area, not per unit volume. It's just the net phi per second. That's what we're after, because on the left-hand side, we had d phi by dt. So we want something that is phi per second, okay? I need to fix a couple of things in the slides, but for a first go, I think it's good. Okay, so let me simplify this a little bit. I know you don't like integrals. We're going to get to them with finite volume, but for now, you don't have to suffer through that. So if the surface is flat and the flux is constant and perpendicular to the surface, then this whole integral simplifies to the flux times the area. Okay, very simply. It's flux times area, because then the flux is constant. You can pull it out. The area is perpendicular to, so the unit normal is aligned with the flux. And so this becomes 1. And so this becomes J times area. Okay? Okay, so now how can we use this to finally tie in the loose ends? Okay, so we're going to take our control volume in 3 dimensions. This control volume it's infinitesimal, but not quite a point yet. Okay, not 0, not very small, not like epsilon. It still has a finite size. It's in the x, y, and z directions. Its length are delta x in the x direction, delta y in the y direction, and delta z in the z direction. Okay, so those are the dimensions of the cube, our control volume. Okay, now there is flux coming in from the left. Could be advective, diffusive, or both. I don't care. It's just flux. What I'm after is figuring out how we can tie in the flux to d phi by dt. That's what I want to get to. Okay? So there is flux coming in the x direction. So that's the x-axis. That's the J1 flux, right? We called the x direction flux, called it J1. This J1 is the x direction flux taking place at location x, some arbitrary location x. And remember, we need to multiply by the area to get dimensions per second. So dimensions of phi per second, right? Mass per second. Okay, good. So that's J1 at x. And I'm going to assume that it exits on that location as J1 at x plus delta x, a small increment away from x. What changed it? I have no idea. And frankly, I don't care because I am after figuring out what that change is. Okay? So you don't asking the question like, what is J1 x plus? I don't know. I am trying to find it, but let's see what happens. Let's do the math and see what happens, right? Because everything is unknown here. But the paradigm shift you need to do is like, you know what? These are just mathematical symbols to get to a point where we can express everything in terms of u, v, w, and p and the quantities that we care about. Okay, so something happened in between that changed this flux, that changed what's coming in and what's leaving. Could have been reactions, could have whatever. Okay, doesn't matter. It's just J1 at x plus delta x, also multiplied by the area. Now you could argue, why is the area the same? Make the area not the same. Just complicate your math. The result will be identical. Okay, there's no point. Make this a pyramid. It's a great homework assignment. Like these, it doesn't matter. You make it a sphere, still doesn't matter. You'll get the same exact result. Okay, this is the simplest way of presenting this. In the same spirit, we have a diffusive flux coming in the y direction, and we're going to call that J2, coming in at some y location, multiplied now by the area. When you multiply by the area, it gives you a rate of phi per second. Okay? And then it leaves as J2 at y plus delta y. Okay? So pay careful attention to that. And finally, same thing in the z direction. You have something coming in and out of the board. Okay? All right. So now, here's the kicker. Our equation that we wrote before, we have to adjust it a little bit. We need to multiply phi by this volume, delta x, delta y, delta z, because that's the net amount of phi in that control volume. Not per unit volume anymore. Now, this is per whatever volume you choose. Turns out that doesn't matter actually at all because everything is going to be per unit volume. And so you multiply by delta phi. So that gives you the net amount of phi per time. Now we can compute the rate in minus the rate out. Now think about it. Why did we write this equation in this way? Now I'm choosing signs. Rate in minus rate out. If everything goes according to what we understand, then if more stuff is leaving, then d phi by dt should be negative. That's correct. If rate in is smaller than rate out, and these are positive numbers, if this is smaller than that, then indeed d phi by dt will be negative. Good. That's why we put in minus out, not out minus in. If what's coming in is larger than what's leaving, then d phi by dt is going to be positive and increase, and that's consistent with this formulation. Okay? Good. All right. Okay, so let's now express the rate in minus the rate out in terms of what? The fluxes. Again, these fluxes are advective and diffusive, or they're the sum of both. Sometimes you might have one or the other or both. Okay? Okay? Now, in the x direction, the rate in minus the rate out is simply the difference between J1 at x, delta y, delta z, minus J1 at x plus delta x times delta y, delta z. Agreed? Because that's a rate. Phi per meter squared dot second times meter squared is phi per second. Same thing for that one. Okay, in the y direction, you have J2 at y minus J2 at y plus delta y. And in the z direction, J3 at z minus J3 at z plus delta z. In minus out. Rate in minus rate out. Okay? All expressed in terms of the fluxes. Now, this way, I don't have to do one for advection, one for diffusion. Once we get the final equation, it will take me 2 slides to do advection and diffusion just by replacing terms. Okay. Now, my next step is to try to express J1 and J2 in terms of phi. Okay, so how do we do that? Well, if you recall Taylor series, that's the benefit of infinitesimal analysis or differential analysis is that this J1 at x plus delta x is not so far away from J1 at x. So could we approximate it somehow using information from J1 at x plus something? Okay. Yeah, indeed, we call upon Brooke-Taylor, okay, Taylor series. F of x plus delta x, any continuous function, is f at x plus delta x times df by dx, the slope, the rate of change, right? So if you know the rate of change, and for a short span, that rate of change is kind of constant, right? So you know that the point at the end is simply the point at the beginning plus the distance times the slope. The slope is rise over run times the run. It gives you the rise or the change, and then you can compute the value at x plus delta x. Plus some higher order terms, which are not going to matter once we shrink everything to 0. You will see these terms are going to be multiplied by delta x squared and delta x, delta y, and so on and so forth. They're all going to go to 0. Okay, so when you apply this Taylor series to J1 at x plus delta x, or J2, J3, etc., you'll get J1 at x plus the distance between this face and that face, okay, times the slope or the rate of change of J1 with respect to x. Because that's what happened. What happened to J1 as it moved from the left face to the right face? It probably changed. Changed by what? By a rate of change. Okay, great. So we'll see what we're going to do with that. All right, so when you do this, something beautiful happens. Because the J1s, they cancel out. The J2 and the J3, they cancel out. And you are only left with rates of change. Rate of change of J1, rate of change of J2, rate of change of J3. And not only that, guys, look at this. Delta x, delta y, delta z, delta x, delta y, delta z, delta x, delta y, delta z, which is what? Delta v, right? OK, so now, then plus higher order terms. Now, the higher order terms, they're going to be multiplied by delta v times delta x, delta v times delta y. So although delta v is going to simplify, they're still going to have a delta x, delta y. And when we shrink to 0, all of those terms are going to disappear. OK? So now you put everything together, and you simplify with delta v and shrink to an infinitesimal point. You get this beautiful equation that the rate of change of d phi of phi over time is equal to the negative sum of the fluxes, of the rates of the fluxes, the rate of change in space for J1, J2, and J3 in all three directions. Gets even better. What is this term? D by dx plus d by dy plus d by dz. That's the divergence, right? That's the divergence. So what this is saying is that d phi by dt, the rate of change of phi, is negative. I hate using these words, but because I want to ask you the question of what divergence means next, because it has a very strict meaning. It helps when you are writing equations to say what you are writing. I don't say d phi by dt. I say the rate of change of phi with respect to time. So I want to remember that has a meaning, not blindly symbols d phi by dt, etc. I'm going to say the divergence of j, but that has a meaning. Okay, I'm going to ask you on the next slide. Okay, and then we're going to add some source terms, and that is going to be our generic balance equation, guys. So we're going to apply this to mass conservation, momentum conservation, energy if you want to, and done, right? It's a balance of fluxes plus some source terms. OK, so now I want to ask you a question. What is the physical meaning of divergence? If you took fluids with me, you better know that answer. It's related to that, but what is like this precise word? So think about this. If more stuff is leaving out of the control volume, okay, then d phi by dt is negative. This means that div j is positive. Agreed? If more stuff is leaving out of the control volume, then d phi by dt is negative. We agree. So if this quantity is negative, then this means that div j must be positive. Okay? The other,
If I remember, it's how quickly or how the rate at which these things are moving away from each other.
yes, yes. So okay. Let me finish. Let me do this. Now the opposite is true. If d phi by dt is positive, this means that this is a positive quantity. So this means that div j is negative. So what this tells us, you can frame it this way. The divergence is the net outflow of information from a point. The net outflow, which is positive. So if things are leaving, div j is positive. So that's the net outflow. There's a net leaving, then net of matter leaving out of the control volume. And then this minus sign adjusts it so that you get a negative rate of change. And if div j is negative, then you recognize that there's a net inflow into my control volume, into my point. Okay? So this is what it looks like. When things are leaving your point or when the vector field is taking matter away from you, then your divergence is positive. So I would say this, that the rate of change of the quantity of information per unit time is equal to negative the net outflow of stuff, right? Because the net outflow is a positive quantity, and you multiply by the negative sign, so then you get d phi by dt negative, etc. Okay. Are we ready for Navier Stokes? Let's do it. Okay, so let's now apply the general conservation to mass and momentum. All right, we start with mass conservation, which says that the rate of mass accumulation is balanced by the rate of mass coming into the control volume minus the rate of mass coming out. Remember, this is our general conservation law. And this is usually called a continuity equation as well in mathematical circles. For mass, phi was equal to rho. And mass enters and leaves the control volume via advection. So that's J is U times phi, or essentially U times rho. There's no diffusion of total mass. Mass does not diffuse unless you have like species transport, but the total mass doesn't diffuse. It's just transported, okay? And then no source terms. So that gives us, if you put rho instead of phi and rho U for J, you get the mass conservation equation, which we call the continuity equation in fluid mechanics. d rho by dt is minus div rho u, or the net outflow of, now you might be inclined to say this is rho u, this is momentum per unit volume, but it's really kind of the net outflow of mass out of a point, okay? So that's our first equation, okay? Now, this is interesting because we started with J's and whatever, all this kind of weird stuff, but now we have equations that relate the quantities of interest, rho, u, and we're going to see P and density next, okay? Well, we have density over here. This is a scalar equation. It's a single equation because the divergence of a vector field is a scalar. Div rho u is d rho u by dx plus d rho v by dy plus d rho w by dz, okay? So brush up on your vector calculus. Okay, let's go after momentum. And I know I botched some definitions here between dimensions of rho and dimensions of phi. I'll fix that in the slides. All right, so momentum conservation law says that the rate of momentum accumulation is balanced by the rate of momentum coming into the control volume minus the rate leaving. Okay, duh. Okay, but momentum is going to advect and diffuse. Right? It's not matter, it's momentum. It's like inertia. But it's also driven by pressure differences across the control volume. So pressure differences across the control volume can try to shrink it or expand it. And then the fluid is going to resist that. If it's compressible, it's going to say, whoa, 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 dude, I'm not going to allow you to compress me. So there's going to be some forces kind of fighting that. But there's also gravitational effects on the control volume. This framework that I presented, this is the only pitfall of it, is that it doesn't do well when you talk about forces. It's not clear, but it gets us most of the way. So there's going to be a statement at the bottom. I'm going to tell you, just accept that as is, okay? And don't ask questions because we need to solve these equations. So for x momentum, we got rho u. Call that phi1. For y momentum, we have rho v. For z momentum, we have rho w. So we'll do the x momentum for now. X momentum enters and leaves the control volume via advection. So the advective flux is u phi, which is u vector times rho u. That's the information for x momentum, rho times axial velocity. For Newtonian fluids, x momentum diffuses according to Fick's law, and that's going to be minus mu grad u. Okay, so this is not really phi, it's phi over rho, but that's what I need to fix in the slides. But this is it for diffusion. That's simplest Newtonian fluid. Okay, for non-Newtonian fluids, this gets weird. You have to consider more continuum mechanics stuff. But from an intuitive perspective, yeah, it's just moving momentum through a gradient, higher momentum to lower momentum. That's all it's doing. That's what diffusion is doing. And then there's a pressure force, which is related to the pressure gradient, dp by dx, across the control volume. And finally, gravitational force, which acts on the entire control volume in the x direction. Let's say there's x acceleration gx, call it. So that gives you the gravitational force. So those are the last two pieces that it's always hand wavy to do it in this approach. If we're doing the other approach, take us 2 months, but we can accept this, I think, reasonably well. At least the units are consistent, dimensions are consistent. So when you do this, you plug everything in, you get your first momentum equation, the axial momentum equation, which is one of the first equations in Navier Stokes. d rho u by dt, the rate of change of phi with respect to time, is minus the net outflow of through convection, right? So this is the convection term. This is J coming from convection, and it's u vector, that's the convective flux, u vector times x momentum. And then here you have minus div minus mu grad u, so that makes it a plus sign. So you get div mu grad u for the diffusion term of momentum. In mechanical engineering, we call this the stress tensor. Okay, this is coming from the stress tensor. It's not a tensor here, okay, but you have to combine all equations together for you to see the tensor. But this comes from the balance of forces and stresses. And then minus dp by dx, which was this force, and plus rho gx. Now, this is written in, this is a scalar equation. Okay? Can you check that for yourself? Just look at one term in it. This is a scalar, right? This is a scalar, so everything should be a scalar. Okay, this is a scalar. This is a scalar, not a vector. Div mu grad, okay, this is a vector, but the divergence of a vector is a scalar. Good. Div u rho u, but u rho u, this is a vector because this is u vector, rho u scalar. So this is a vector. Div of a vector is a scalar. And let me show you what that looks like. So div of u rho u, and here's a little trick how to interpret these terms. If you treat the nabla term, the nabla operator, this inverse delta, if you treat it as a vector or an operator vector with components d by dx, d by dy, d by dz, you can just simply dot it with any other vector as a dot product. Okay? So now you're dotting nabla, this dx, ddy, ddz, with rho uu, rho uv, rho uw, the three components of this vector. So you get d by dx of u rho u, d by dy of v rho u, and d by dz of w rho u. Just a simple dot product between two vectors. So treat nabla as a vector. It simplifies things a lot. Same thing here, expand this guy and then do the dot product of two vectors. Okay? Similarly for y and z momentum, all you have to do is replace the meaning of phi. You have rho u here, you have rho v, rho v, rho v, 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 dp by dy, rho gy. Same thing for z momentum. Okay? There you go, Navier Stokes. Why didn't we do that in fluids? Okay. And this gives us most of the set of equations for kind of general gas dynamics. I made strict assumptions. So these would apply for a general compressible flow. Okay, except this might not be 100% accurate here, because assuming Fick's law also makes some assumptions about incompressibility for the fluid. But if you accept this and say, the effects are minor over there, these are the full gas dynamics equations for compressible flow, for general gas dynamics. They're missing something, though, okay? So we have, count with me, 1, 2, 3, 4 equations, but we have 5 unknowns. So if you look at our unknowns here, we don't know what rho is. We don't know what the velocity vector is. So rho, the velocity vector is UVW, and we don't know what P is. Mu is a property of the fluid that's usually given to us, and G is gravity, right? So we don't know what P is. So we have 5 unknowns, but 4 equations. So we are missing 1 equation, okay? And specifically, there's no equation for the pressure. Now, this is where physical insight comes in, okay? If you're thinking about compressible flow in general gas dynamics, then you could argue that the pressure can be related to the density via an equation of state, P equal rho RT over M, right? But you then need a temperature. So if you say P is a function of 2 thermodynamic variables, that's the rule, right? Pick rho and T. Okay, so then you get rid of P, you express it in terms of rho, but you introduce a new variable called T. Well, then we need an energy equation. We derive an energy equation. From the energy, we can deduce a temperature, and then we have a fully closed system of equations. Okay, I'm not going to derive that because we're not going to do gas dynamics now. Okay, so this set would give you the general gas dynamics equations for compressible flows. Okay, but there's another issue which is more interesting to us now. What if the density is constant or the flow is incompressible? I'm going to take the worst case, which is the density is constant everywhere, the simplest case, because you could have density changing while the flow is being incompressible. So water droplets and oil droplets, you're shaking them in a balloon. It's incompressible, but you have changes in density throughout, okay? So you could have variable density, but incompressible flow. The strongest simplification is a constant density everywhere. So with a constant density everywhere, physically what that means, you no longer have an equation of state, because if the density is constant, it's not responsible for changes in the pressure. The temperature is not even responsible for that either. So pressure and density are completely decoupled. And if you look at the definition of the speed of sound, for incompressible flows, essentially the speed of sound is infinite. And you can use that equation to show that there's no relation. The relation between pressure and density becomes invalid, entirely invalid. So there's no equation of state anymore. So the pressure is no longer a thermodynamic quantity. Okay, so that's one way to kind of eliminate. So we make the density constant. But the problem now is we don't have an equation for the pressure anymore. So the equation of state is no longer valid because changes in pressure do not cause changes in density and vice versa. So here's what happens to the set of equations. With constant density, we start with mass conservation. d rho by dt is minus div rho u. Well, d rho by dt is 0 because rho is constant. And this guy, div rho u, is rho div u plus u dot grad rho. Okay, so you think about the math in your mind. So if grad rho is 0, that entire equation simplifies to the statement that div u equals 0. Okay? The net outflow of u, or momentum per unit mass, is 0. So the meaning of this, and there's a nasty derivation to show the statement that I'm going to say now. This is equivalent to the net outflow of fluid volume is equal to 0. So what is essentially saying, you cannot change the volume of a fluid when this condition is satisfied. So, which is consistent with incompressibility. You cannot change the volume of fluid particles. They're incompressible, right? That's what this means. Anyway, we just take it as this. We say div u equals 0, or the dilatation equal to 0. Okay? So that's what happens when the density is constant. Now it's no longer a time-dependent differential equation. It's just div u, right? It just depends on space. Has nothing to do with time. Okay? Whereas this equation had density change with respect to time. All right, so now what happens to the momentum equations? If rho is constant, I'm going to take it out and divide everywhere by rho. And I'm also going to assume that mu is constant for incompressible flows. I mean, it's a very reasonable assumption to say viscosity is constant, unless you have like extreme changes in temperature. Then viscosity is constant. You can pull that out. And what happens is, okay, we start with x momentum. So rho comes out, divide by rho everywhere. So I get rid of rho here, get rid of rho here. I have mu over rho. So I have a typo here. This should be mu over rho. And I have 1 over rho times pressure gradient plus gravitational term. And notice what happened here. So this becomes div of u times u. This is still a vector, okay? And here I have div grad u. So when you take mu out, you have div grad. And div grad is the Laplacian. Okay, it's del squared operator. Okay? So second derivative. Same thing applies for y and z momentum, and you get your 3 momentum equations, and those are the Navier Stokes equations. Okay, there's a typo here, mu over rho, mu over rho, mu over rho. Okay? Those are the Navier Stokes equations. 4 equations. Let me see. Yes, 4 equations. And 4 unknowns. So now we took out the density. It's no longer an unknown. So we have enough equations as we have unknowns, right? Previously, in the previous case, we had rho, u, v, w, and p. We had 5 unknowns. When we take out rho, we still have u, v, w, and p. And we have 4 equations, not equation. 4 equations. But there's no equation for the pressure. I mean, the system is well posed in the sense that we have enough equations as we have unknowns. But there I have, how do I compute the pressure? Like, what do I use this equation to compute the pressure? Why not use this one? Why not use this one? What about UVW? I can't use this one to get UVW because this has all 3. What? It doesn't make sense, right? And that's one of the tricks I mentioned last time. It's like that was huge in the development of methods to solve these equations, because the pressure, turns out, is like embedded in that mass conservation equation. The pressure, I'm going to say on the next slide. So note, the equation of state doesn't apply, like I mentioned. Okay? So in fact, the pressure here plays a role unrelated to thermodynamics. Has nothing to do with thermodynamics anymore. Okay? From a purely mathematical perspective, the pressure is actually a Lagrangian multiplier to force the momentum equations to conserve mass. That's what it does. Now, physically, what it's trying to do, it acts to either accelerate or decelerate fluid particles, and it helps specifically to help combat accumulation or depletion of fluid particles to make sure incompressibility is satisfied. So P is strictly used to make sure that div u is 0. So if fluid is trying to converge to a point, you're going to see high pressure. You go and run an experiment or get a CFD calculation. And you'll see that whenever the flow is trying to converge, you get spikes in pressure. And whenever the flow is trying to leave, the pressure decreases to try to bring in more flow. Okay? So it's trying to balance that. It's trying to play that game. Okay? All right? Finally, the equation set that we will be working with is going to be in 2 dimensions. So we're going to knock out the z direction, constant density, and I'm going to expand all the terms. So we have continuity, or the mass conservation. So that's div u equals 0, du by dx plus dv by dy equals 0. So in 2D, we only have u and v velocities. X momentum and y momentum. X momentum, change in u with respect to time. This is the convective flux. I split it into 2 terms. You have uu and vu. Okay? And then the diffusive term, second derivative, so that's the Laplacian of u. Second derivative of u with respect to x. Second derivative of u with respect to y. Pressure gradient and gravity. Now, same thing here. Okay? Now, when you look at this, you see some beautiful symmetry. You get uu, vu, uv, and vv, for example, here. Now, when you think about this advection term, always think of 2 things. What is the information being advected? And what is advecting that information? So strictly speaking, from an accounting perspective, the x momentum equation deals with x momentum, so that's related to u. So over here, the information I'm transporting is u by advection. So u. What is transporting u? In this term, u is transporting u, v is transporting u. So imagine that. X momentum is being transported by x velocity and y velocity. Same thing here. Y momentum, v, is being transported by x velocity and y velocity. It's coming from all directions, right? Because momentum is information. Velocity is just a property of the fluid, right? It just happens that momentum is related to velocity. So that's why you get this u, uv, etc. And I mentioned the price to pay when we go to a Eulerian perspective is this nonlinearity. Because yes, these equations are coupled, but they're coupled in such a nasty nonlinear fashion. U is multiplied by u, and u multiplying v. So like this entire equation is embedded here in this term. Can you imagine that? And this entire equation is embedded in this term here. So these are the nightmare for Navier Stokes, because these terms are linear. Second derivative is linear. So if there was no convection, we could find like easy analytical solutions for these. Stokes flow, right? Purely diffusive flow. Okay? We're going to spend considerable time solving this set of equations. Okay, we're going to learn how to untangle the pressure out of this. And the strategy is going to be what we call the method of lines. And that's essentially every time you have a differential equation, you are going to solve for the quantity under the time derivative. So we use this equation to advance x momentum in time. We use this equation to advance y momentum in time. And we're going to use this equation to figure out the rest of the unknowns. Okay? So when I look at this, I'm like, yeah, I can solve this for u. I can solve this for v. And the other one, I'm going to use it to figure out what to do with p. Okay? When I say there's no equation for p, there's no transport equation for p. There's no rate of change of p, right? There's no dp by dt term, an equation like that, right? Because when we set out to write this equation, we said d phi by dt is equal to something. So we're really after phi. So if you think about it, this is the equation for x momentum. This is the equation for y momentum. We're going to use this to solve for x momentum, use for y momentum. Okay? And that's it. Done in 1 hour and 8 minutes.